Section 3.4, zeros of polynomial. For a polynomial, the rational root theorem says that any rational roots must be factors of the constant term a sub 0 divided by the positive factors of the leading coefficient a sub n. By using synthetic division, you can find enough roots to factor the polynomial to linear factors and also maybe a quadratic. And then once you have a quadratic, you can use whatever method you want to solve the quadratic. Well, whether it's maybe it factors, complete the square, quadratic formula, factor by grouping. You can also do that. Doesn't even have to be a quadratic to do that. So in this example that I have here, x to the fourth minus 11x squared minus 18x minus 8 is equal to 0. My a sub 0, that's your constant term. What is it? I hope you can see that it's negative 8. So what you're going to do is take the factors of negative 8. So plus or minus 1, plus or minus 8. Because 1 times 8, with one of them being negative, if you multiply it, equals negative 8. Also, 2 and 4. So positive negative 2, positive negative 4. So all the factors, rewrite them, plus or minus 1, plus or minus 2, plus or minus 4, plus or minus 8. A sub n, that's my leading coefficient. So here's my leading term. My leading coefficient is a number in front of there. It's implied that the number is 1. So the positive factors of 1 would just be 1. So then what you do is divide the plus or minus 1, 2, 4, and 8 divided by 1. And you end up with plus or minus 1, plus or minus 2, plus or minus 4, plus or minus 8. So now I can use synthetic division. Remember, if it's a factor, this number right here will be a 0. Also remember that that is also p of a. So I could plug in my number and come up with that last number there. So let's plug in 1. Instead of doing synthetic division, if I plug in 1 for x, you can easily see that it's not equal to 0. So I'm not even going to do synthetic division there. So I'm getting rid of that one. So let's try negative 1. Bring down my 1. 1 times negative 1. Add. Multiply. Add. Multiply. Add. Multiply. And lo and behold, it is a factor. So my x to the fourth now, I brought it down to an x cubed. So what I'm saying is this factors into x plus 1 times x cubed minus x squared minus 10x minus 8. So now from there, you might want to reevaluate, but this is still an 8, so those are still the rational possibilities for rational roots. But if when you factored it, and if this weren't an 8 anymore, if it were like a 4, you could automatically get rid of 8s. Because you know 8 wouldn't be a factor of that anymore. So now I have my x cubed. And since 1 didn't work first, it'll never work. Negative 1 could work more than 1, so you could even try negative 1 multiple times if you want. Or you could try a different number. It does not really matter. Let me try negative 1 again, just in case that might work. I don't know if it does or doesn't. So let's go. Negative 1. Bring down my 1. Multiply. Add. Multiply. Add. Multiply. And it does work. So now I know that this factors into an x plus 1 and an x plus 1. And also, this was an x cubed, remember? So now I'm down to x squared. So x squared minus 2x minus 8. Now, the quadratic that I have, the squared, can we factor that more? And I hope that you can see that it does factor additionally. So let me rewrite it. X plus 1, I'm going to write as quantity squared. That's that and that. My x squared factors into 4 and a 2 with one of them being negative, and I hope you can see that the 4 is negative. So there it factors. So on the problems, you are going to factor completely like this. I might ask you what the roots are, and you would tell me the roots are negative 1, negative 2, and 4. Negative 1's a double root. So those are the rational roots. I might ask you to graph that. So you'll need to use this to factor, and you'll graph. And we graphed a couple sections ago, so you might have to graph that. So make sure you remember from a couple sections ago how to graph. If you don't remember, go watch 3-2 video again, because you will have to graph in this section, and I'm not going to do it again. Just watch 3-2 video if you need to do it. And I basically finished this, so I don't need that one. So according to the rational root theorem, I want to know what the possible rational roots for each equation are. So all I'm asking you are the rational roots. Not going to ask you to factor this one, I just want to know the roots. So I would take the factors of negative 4, 1 times 4 and 2 times 2. I would take the factors of 2, 1 times 2, and I would divide them. So I would have 4 divided by 2. Here, I'm going to write them out this time. Actually, I'll do it by 1 first. 4, 2, and 1 divided by 2. So plus or minus 1, plus or minus 2, and plus or minus 4. That's this divided by 1. Now, if I do that divided by 2, plus or minus 4 divided by 2 gives me 2. I already have it. Plus or minus 2 divided by 2 gives me 1. I already have it. Plus or minus 1 divided by 2, that's the only one I don't have. So plus or minus 1/2. So plus or minus 1, plus or minus 2, plus or minus 4, plus or minus 1/2. Those are the possible rational roots. If I was going to do B, factors of 5, plus or minus 1 and 5. Factors of 6, 2, 1, 3, and 6. So the possible rational roots would be, I'm going to divide by 1 first. So plus or minus 1, plus or minus 5. And now I'm going to divide by 2. Plus or minus 1/2, sorry, plus or minus 5/2. Now I'm going to divide by 3. Plus or minus 1/3, plus or minus 5/3. And now I'm going to divide by 6. Plus or minus 1/6, plus or minus 5/6. So those are your possible rational roots. And if I asked you to factor it, you can use rational root theorem and see if that last number is a 0. Remember, if it's a 0, it is a root. If it's not a 0, start from the beginning, the drawing board, and try again. The conjugate pairs theorem for irrational zeros says that if p of x is a polynomial function with integer coefficients and a plus b, the square root of c, where a, b, and c are integers and c is greater than 0, is an, not an irrational 0 of p of x, then its conjugate is also an irrational 0. Okay? So if 1 plus 2 square root of 3 is a root, then 1 minus 2 square root of 3, which is its conjugate, is also a root, or a 0. Descartes' rule of sign says for a polynomial f of x with real coefficients and terms written in descending order, the number of positive zeros is either equal to the number of variations of the sign of your f of x or less than that by a number by an even integer. And I will do some examples so you'll understand what that says. The number of negative zeros is, I find f of negative x, and I find the variation in sign of that, and that also is the number or that less by an even integer. Okay? And multiplicity m should be considered as m zeros. So if 1 has a multiplicity 2, then that will be 2 different zeros. So determine the positive and negative zeros of g of x. And this is sort of like the number 33 through 45. I have my polynomial there. When I look at the signs, this is a positive, this is a positive, this is a negative, and that is a negative. So I have my signs. Plus, plus, minus, minus. I hope you can tell right here, that right there is the only variation. So your variation in sign is just 1. So the number of positive zeros is just 1. I can't subtract an even number from that because that would give me a negative number. So it's just 1. If this had 5 changes, then the positive number of zeros would be 5 or 3 or 2. Or 1. You're subtracting 2 every time, an even integer. Now, plug in g of negative x. So plug in negative x for your x. And when you plug it in, you'll have, so that's what you're doing first, plugging it in. I guess I wrote it all out. When you plug in a negative here, you have negative 3x cubed. Here I'll still have plus x squared. Here I'll have a plus 9x and minus 3. So now you can see my signs are positive, negative, negative, positive, positive, negative. So here's a change in sign, and here's a change in sign. So the number of variation is 2. So the number of negative zeros is either 2 or 2 minus 2, which is 0. So 0 or 2. And that's how Descartes' rule of sign works. You try this one, pause it, try it yourself. So using Descartes' rule of sign, let's see if you got it right. There's my polynomial. My signs would be negative, positive, negative, negative, positive. I hope you can tell. There's a variation in sign, there's a variation in sign, and there's a variation in sign. So there's 3 variations in sign, so the positive zeros will either be 3 or 1. If I plug in a negative x, you'll have positive 5x to the 5th minus 3x cubed plus 2x squared plus 7x plus 4. So now my signs for the terms would be positive, are positive, negative, negative, positive, positive. There's the change, there's the change. So there are 2 changes in sign, so it's either 2 or 2 minus 2 is 0. So 0 or 2 negative zeros. And this might help you when you look at that, because then you'll know with the synthetic division whether to try a positive root or not. There are 0 changes in signs. If they're all positive numbers, don't try a positive number with synthetic division. It won't work because there would be 0 sign changes, 0 positive roots. So that might save you some time. If a polynomial f of x has no zeros greater than a number k, then k is called an upper bound. So what they're saying is, you basically have some polynomial here. Here's my polynomial. They're saying that number, whatever that k is, that's an upper bound. There's no 0 that's larger than that. This one right here is a lower bound. There's no 0 that's smaller than that. So that's all they're saying. F of x is a polynomial with real coefficients and a positive leading coefficient. Suppose f of x is synthetically divided by x minus k, then if k is greater than 0 and each number in that last row of synthetic division is a 0 or a positive, then k will be an upper bound. If k is less than 0 and the numbers in that last row alternate signs, plus, minus, then that's a lower bound. If there's a 0 in that last row, you can call it whatever you want, a positive or a negative, to make the signs either all positive or alternate. Okay? So remember, upper bound, the positive one, all has to be zeros in that last row are positive. For the lower bound, that last row has to be alternating signs. And remember, 0 you can handle any way you want to make it fit the rule. So these are like 47 through 54 in bounds. Find the upper and lower bounds on the zeros of, and there's my polynomial. So when you're looking at that, notice there's only one sign change. So there's really only one positive 0. And if I do negative x, there are 3 sign changes. 1, 2, 3. Okay? So for the negative, there are either 1 or 3 negative zeros. So by the rational root test, we can take the factors of negative 5 and divide it by the positive factors of 6. And we have our possible zeros. And then let's figure out what are, if something's a bound or not. So I'm going to start with the positive numbers. If I start with 1/6 and do synthetic division, remember that all these have to be positive numbers. So you can start doing synthetic division. 6 times 1, 6 is 1, add, multiplying it 4, add, multiply. And I hope you can see that this right here is 4 point something. You don't even need to figure out what that is. Positive 4 point something plus a negative 9, I hope you know that gives you a negative number. So you don't even need to calculate this negative 7 halves. You just need to know it's a negative number. It doesn't follow the rule that it's all positive. So that's not an upper bound. So let's keep going. 1/3. If you do 1/3, you're going out a little bit. Do the same thing. And you get a negative number again, so that's not an upper bound. So let's go to 1/2 also. And when you do 1/2, you get all the numbers are 0 or positive. So 1/2 is an upper bound. So when I'm graphing the polynomial, wherever that, if that's 1/2, that's a bound. So it's not gonna, there's not gonna be any place where it crosses the axis to the right of that. That's a bound. Okay? You can do the same thing with the negative numbers, and really you should start closest to 0. I didn't always, but you really should, and work your way out. And when you do that, you can see that negative 5, and I have the work on you there for you. Negative 5, alternate signs when you do synthetic division. Positive, negative, positive, negative, positive. So that one is the lower bound. If I would pick a larger number than negative 5, it would do this also. If I picked, let's see what else there is. Oh, negative 5 is the largest one. But if there was another number larger, like negative 10, it would work for the largest number too. That's why you start in and work out. Okay? You could skip a few and then work back if you want. And I think that's actually what I was doing, because I thought, oh my gosh, look at all those fractions I have to go through. So I think I skipped to see if I could find one that wasn't a lower bound. So find the upper and lower bounds for g of x is equal to x cubed plus 3x squared plus x minus 4. So I want to find the upper and lower bounds on those zeros. One sign change, one positive. For negative x, when I plug that in, you'd get negative, positive, negative, negative. So there are 2 sign changes. So there are 2 or 0 negative zeros. Okay. So the possible rational roots would be plus or minus 1, plus or minus 2, plus or minus 4, divided by 1. So those are my possible zeros. So I should have this for you already on your notes. You can work on it and see, but when you try those, I tried 1, all positive in synthetic division. These are all positive. So that is an upper bound. With the negative, I could already tell that it wasn't going to be alternating signs when I just did 1 and 2. So I stopped. Here, already you can tell. You don't need to go on with any of them. Okay, I don't know why I wrote this here. Sorry. Okay, so you could already stop. But when you do -4, you can see that it alternates signs. So -4 is a lower bound. The homework is 1 through 6 all, 5 through 54 odd, 55 through 74, every other odd, and 77. And like I said, be careful, because I didn't do examples of everything, but for example, you're going to graph each polynomial here. You're going to factor it. You're going to use the rational root theorem. You're going to find the possible roots here. And then you're going to factor these completely. Once you factor them completely, you will graph them.